Good afternoon, everyone. Hi, I'm Jess Stephenson. I'm an assistant professor at the University of Pittsburgh, and today I'm going to talk to you about some of our work trying to understand infected host behaviour. So I think the last year and a bit have shown us how important it is to understand infected host behaviour in order to understand and hopefully control how parasites and infections spread through populations. But my title probably gives you the impression that there's a lot of potentially interacting factors that affect how infected hosts behave. And I would agree with that assessment. And I've been working with Jim Edelman at the University of Memphis to try and distill down this complexity into a framework that we can use to try and understand infected host behaviour moving forward. And both Jim and I work on socially interacting hosts and their socially transmitted parasites, which is quite a specific context. And so in order to kind of bring you along to our way of thinking, which is of course my evil plan, I'm going to start the talk with a brief overview of the system that's informed a lot of my thinking to give you some concrete examples. Then I'm going to describe our slightly more abstract framework and then give you some data from our lab trying to address some things that framework brought up. So, in general, I would say that it's likely that how an infected host behaves critically affects its own fitness. So this is probably not a surprise at this point in the symposium, but of course animal behaviour critically affects both the survival and reproductive components of an animal's fitness, and infected hosts are often no different. So if we start thinking about guppies, and in this illustration we've got males at the front and females at the back. And in guppies, one specific behaviour is activity level. And in general, the more active you are as a guppy, the more attractive you are as a social and sexual partner to your conspecifics. So that means that active guppies are more likely to be found as members of groups, which gives them the advantages of, more effective anti-predator defence, more efficient foraging, more mating opportunities, etc., etc. So in general, if you're a guppy, being more active is generally better. But what does that mean for the parasites? Well, the parasite I work on is Gyrodactylus. It's in this illustration here, and it's directly transmitted when hosts come into close social or sexual contact. So you're probably way ahead of me here, but if you're a parasite, then your fitness also critically depends on the behaviour of your host. And in this instance, the more active the host is, the more likely they are to provide you with your transmission opportunities, which is a key component of your fitness as well. So we can add that infected host behaviour critically affects the fitness of parasites as well. But as well as how this infected fish is behaving right now, we also have to consider how its behaviour may have changed. Because in social groups, everybody's paying attention to everybody else all the time, and any huge changes in behaviour are likely really reliable cues of potentially contagious infections, and everybody else is going to just avoid this female. So not only does her current behavioural expression affect her fitness, but so might the way that it's changed recently. So this is kind of where we think for part of this framework. And so now I've given you some concrete examples to think about as we go through this conceptual figure. So here on the y-axis is the fitness enhancing behaviour or activity level, and on the x-axis is pathogen load, or the number of worms infecting these fish. And here we've got a triangle host and a circular host. And as we talked about, their current behaviour expression is important to their fitness, but as is how much this has changed over the course of infection. So here, the behavioural expression of these hosts before infection is represented by the points on the y-axis, and we can look at how much that behaviour has changed over the pathogen load as our measure of behavioural tolerance. And we really think that both behavioural tolerance and current behaviour are likely to be important to the transmission of the parasite, which we've represented with this beautiful purple shading. And the deeper the purple, the higher the transmission probability for the parasite from that host, or the higher the host competence. So we think here that this triangular host, with its relatively high pathogen load and relatively high expression of activity level, is likely to transmit the parasite more than this circular host. And so in my lab, we started thinking about how we might be able to predict who in the population would behave more like the triangular host and who more like the circular host, because if we can predict who is more likely to transmit, then we can hopefully control that transmission. The first thing that we thought about was tissue-specific tolerance. So by this I mean all of the components of tolerance except for behaviour, which people typically represent on figures like this. So on the y-axis here we have tissue maintenance, and on the x-axis pathogen load. And a highly tolerant host would see a relatively shallow slope here, which would mean that they, for example, lose relatively little mass or show relatively low levels of pathology as a result of their infection. Whereas a host with low tolerance would show dramatic decreases in mass, for example. And we suspected that if you're able to maintain your mass or you show low levels of pathology, then you may well be able to maintain your behaviour as well. Because of this supposition, then we also thought that females are likely to act more like the triangle and males more like the circle, because in this system, females are more tissue-specific tolerant than males. And finally, we also suspected that social context could affect this, because in a number of systems now, it has been demonstrated that host behaviour alone can be quite different to host behaviour with conspecifics. And specifically, a lot of animals seem to be able to fake behavioural tolerance depending on who they're with. So we suspected that even though, for example, this circular host shows quite a steep decline in activity level, it could sort of fake it for a little bit. So these are the predictions that we had and that we tested with the system of the guppy and its Gyrodactylus parasites. So I've already introduced this a little bit, but the host is really enjoyable to work with, but in no way is it as exciting as the parasite. So this is Gyrodactylus in all its glory in this video. And as you can see, it's an ectoparasite, which means that it's relatively easy to quantify how many worms an individual fish has during the course of its infection and keep the fish alive. And that number is likely to change because the parasite is viviparous. So here in this image, you can see a mummy worm who's about to give birth to her baby, and the baby will just latch on to the fish next to the mum. And the parasite is directly transmitted. So as I talked about, when fish socially or sexually interact, the worm will just move across and begin reproducing on the new host. So this system we use to address what factors affect the behaviour and behavioural tolerance of infected hosts. So here's some representative data. On the y-axis is the number of parasites on individually housed fish, and on the x-axis is the day of that fish's infection, and each curve represents data from a different fish. And you can see, so these are individually housed fish, and you can see that there's a huge amount of variation between and within fish in their infection loads. We measured their behaviour at the pre, early and late infection stages. And the behaviour that we measured was an assay represented here. So we had a central focal tank into which we put a focal infected fish that was either male or female. And then we had two stimulus tanks either side of this central tank, into which we put a shoal or nothing. And we measured the current behaviour of that focal fish as the percentage time actively swimming at the early and late stages of infection. And we also measured the behavioural tolerance as the per parasite percentage change in time swimming in early and late while controlling for its pre-infection behaviour. And we also manipulated the presence or absence of the shoal as a way to test for the importance of social context. So our first result is that the fish's current expression of behaviour depends on tissue-specific tolerance, sex and social context. So here on the y-axis, on the x-axis, we have our per parasite percentage mass change over infection, which is our metric of tissue-specific tolerance. And as you move along the x-axis, the fish become more and more tissue-specific tolerant. And on the y-axis, we have the percentage time swimming, our measure of its current behavioural expression. And you can see here that females, there's no pattern among them, there's no correlation at all. Whereas among males, those males that are the least tolerant in tissue specifics also showed the lowest level and quite a dramatically low level of activity compared to males that showed the highest level of tissue-specific tolerance. But interestingly enough, when in the presence of a shoal, these males are able to completely kind of match the activity level of those males that even gained mass during their infection. So this result together suggests that male guppies may use behaviour to conceal their disease and therefore potentially boost their transmission competence. Then we move on to the behavioural tolerance results, which also depends on tissue-specific tolerance, sex and social context. So on the x-axis again we have our measure of tissue-specific tolerance, and on the y-axis we have our per parasite change in the percentage of time swimming, which is our measure of behavioural tolerance. And you can see here that there's a striking difference between females and males. Females again show very little correlation, and males show a strikingly positive correlation between these two components of behavioural and tissue-specific tolerance. And so because it was such a big striking difference, I got pretty excited, and largely because of this paper by Edelman and Hawley, so you may be thinking, well, the sexes differ in the correlation between tissue-specific and behavioural tolerance, so what? What does that actually mean? And it is hard to think about, but Edelman and Hawley have done the heavy lifting for us. So here, they suggested that tissue-specific and behavioural tolerance could either be positively correlated, like we saw in males, or there could be no correlation, like we see in females. And they suggest that this difference is likely to translate into a difference in the sex's contribution to transmission. So again, in this figure here, we've got transmission on the y-axis and then behavioural tolerance on the x-axis. And where tissue-specific and behavioural tolerance are positively correlated, they predict a curvilinear relationship, whereas if there's no correlation, there's a linear relationship. And so there's likely to be several points where the difference between the sexes would lead to females being way more likely to contribute to transmission in this system, which was super exciting to me. I got into this like crazy spiral of excitement, and then I realised that there's no shoal. So who are they going to transmit to? It's completely irrelevant. They're just in a tank on their own. And in fact, when you add a shoal, again, this correlation or difference in correlation completely disappears. So bummer. But the correlation suggests that females are more competent, but again, the social context eliminates this sex difference completely. And so, yes. So to return to our predictions then, we predicted that tissue-specific and behavioural tolerance are positively correlated. And we found evidence that indeed they are in solitary males, yes. We also predicted that females are more behaviourally tolerant than males, and we didn't really see any evidence for this. We didn't see any striking sex difference in our actual values of behavioural tolerance, but we did find that female behaviour is independent of tissue-specific tolerance. So this may suggest that female behaviour is less likely to change as a result of infection, but yes, we still need to dig into that a little bit more. And we finally predicted that infected hosts can fake behavioural tolerance in the presence of conspecifics. And we did find some evidence for this, although only in males. But I think that this could again be reflective of the difference between males and females in how much their behaviour is affected by infection. So in overall summary then, I would say that it is very useful to think about infected host behaviour and behavioural tolerance separately. So in our example, the patterns in behaviour and behavioural tolerance are very similar, although they're slightly nuanced. And it's interesting to think about their relative importance. Because these two aspects may affect host and parasite fitness in different ways. So for example, if social ostracism would affect host fitness more than parasite fitness, then the parasite may only care about current behavioural expression, while the host cares more perhaps about behavioural tolerance. our data suggests that the least tolerant males in the population use behaviour to conceal disease, which may potentially boost their transmission competence. And we found that social context obscures the sex difference in the behavioural and tissue-specific tolerance correlation. So to sum up then, I think our data clearly indicate that males are dirty lying cheats, as we all knew, and that behavioural differences may make the sexes very different resources for the parasite in terms of the transmission opportunities they represent. And I'm really excited to kind of dive into what this could mean for the co-evolutionary dynamics between host and parasite next. So all that remains is for me to thank you for your attention in this very complicated, bamboozling talk. Sorry about that. And also to thank the undergrads who helped me set up my lab and were instrumental in this project and were co-authors on the paper we just submitted. My other lab members who've been great, my postdoc lab at Jim, and also my funders. And I'll happily take any questions. Thank you.